Hello everyone, my name is Aarohi and welcome back to my channel. So guys, on this channel, I try to break down complex topics. I try to explain them in the simplest possible way. So if you think that this content is valuable, if you think that this content deserves it, then please like the video, share it with your friends and subscribe to support the channel. Thank you for listening and now let's start with today's topic. So guys, in our last class, we learned how to prepare input for transformers. So for that, first we used a tokenizer. We used it to break the raw text into tokens. Then tokenizer assigned a unique ID to each token. After that, these token IDs were then passed into the embedding layer, which created a vector for each token. And after that, we used positional encodings. We use positional encoding to add the position information of each token. And for this, we created our positional encoding vectors for all the tokens. And then we performed a element wise addition between the embedding vector and the positional encoding vectors. And after this step, now our input is ready. We can give this input to the transformer and this matrix will be the input to the transformer. And guys, if you are watching this lecture without going through the previous two lectures, then I strongly recommend watch those videos first because this video is based upon those two lectures, those previous two lectures where we understood the concept of tokenizer, embeddings and positional encodings. And guys, before we move forward, I just want to discuss few things about vocabulary also. I know we discussed this in the last class as well, but before starting today's lecture, I want to clear few more things, okay? So, what is vocabulary? Vocabulary means the set of unique tokens which are created by the tokenizer when it is trained on a large raw text dataset. And we collect this raw dataset from various sources like books, websites, and databases, right? And these tokens can be words, subwords, characters, or punctuations. And if the tokenizer learns 50,000 unique tokens, then the vocabulary size will be 50,000. And if the tokenizer learns 30,000 tokens, then the vocabulary size will be 30,000. Vocabulary is created during tokenizer training. And tokenizer training happens before transformer training. And now guys, I want to discuss few things about embedding layer as well. So some of the content may feel repetitive, but don't skip it because there are few new points I have added in this explanation which you need to understand, which you need to know before learning the transformer concept. We know that token IDs produced by the tokenizer are given as input to the embedding layer. Then the embedding layer contains a lookup table of shape, vocabulary size into D model. And if the vocabulary size is 50,000 and D model is 4, then the embedding table has 50,000 rows and 4 columns. And if the D model is 4096, then the table will have 4096 column. And in this matrix, each row represents one token and it stores the embedding vector, right? And these vectors are randomly initialized using a uniform or Gaussian distribution at the beginning of the training. And then these parameters, these are basically learnable parameters and model learn these parameters with time. And during training, the values of these embedding vectors change. They learn the semantic meaning of the tokens. And after the transformer model is trained, when we give a new input sentence, such as our input sentences, my name is Aarohi and I love coding. Let's say once your transformer is trained, your embedding model is trained, it has a lookup table now. Now we are giving it a new input sentence, which is my name is Aarohi and I love coding. The tokenizer will convert it into 8 tokens. Then the embedding layer will look up only these 8 tokens from the embedding table and it will produce an embedding matrix of shape 8 into 4. What is this 8 into 4? 8 is the vocabulary size because our input sentence is this. And how many tokens are there? 8 tokens. Tokenizer created 8 tokens. So this embedding size shape is vocab size into D model. So for this example, you're going to have an embedding matrix of 8 into 4. 4 is the D model and 8 is the number of tokens we have in our input sentence. But guys, remember now, at this time, it is not learning. Okay, when you gave this input sentence, your model is not learning. It learned the embedding at the time of training, but now we are giving this input sentence and we want a transformer to work on it, to process it and generate some output. Okay, so this time when you give this input, it is not learning anything. The embedding layer is only creating embedding metrics for these 8 tokens. It will see the embedding table, okay, lookup table, and it will pick the 8 tokens which are there in our input sentence, and it will create a matrix of shape 8 into 4. So it is not learning, it is just using the embedding table that was already learned during the training phase. So it simply looks up the rows which represents the token IDs which are present in our input sentence, and then it will create an embedding matrix of shape, of size 8 into 4, because we have 8 token in the sentence and the D model is 4, which means 4 columns. And once we get the embeddings for our tokens, the next step is to add positional encoding, and I have already explained you the full concept of positional encoding, so please check that lecture if you have any confusion. In short, positional encoding tells the transformer about the position of each token in the sentence, and the positional encoding vectors will have the same shape 8 into 4, and after that we will perform element wise addition, and this final matrix becomes the input to the transformer's encoder. And guys, always remember, vocabulary size decides the size of embedding table. If you want to write it this somewhere, write it, because in some time we are going to study about different things. There are going to be different shapes and sizes of different topics which we are going to discuss. So just remember for now that the vocabulary size decide the size of the embedding table. Okay, what does embedding vector tells? Embedding vector tells what the word is. It will tell you the semantic meaning, and positional encoding vector tells where the word is, the position of that word. And now we are going to study about encoder. And what will encoder do? What will encoder learn? Encoder will learn how word relate to each other. And guys, today what we are going to learn? We are going to see how encoder will learn how word relates to each other. Okay, this is what we are going to learn today. So let's understand the encoder. So encoder is the starting point of the actual transformer work, and transformers have encoders and decoders. And in the paper, attention is all you need paper. So they have used 6 encoder layers, means 6 encoders stacked one after the another, and all these encoders work in the same way. So if we understand the working of one encoder, so we will automatically understand how all other encoders work. And encoder tries to learn how words relate to each other, and one encoder layer has two main parts: multi-head self-attention, and the second one is feed forward neural network. Plus, it has residual connections and the layer normalization. We will discuss all these things in detail step by step. Right now, I'm just giving you the overall idea of what all things we have. Okay. Now, let's start with multi-head self-attention layer. Let's try to understand this concept, how this layer works. So, what does attention mean? Let's start with the basic. Let's understand what does attention means. So, attention means focusing on the most relevant words while processing a particular word. It allows the model to decide which word in the sentence are important for understanding the current word. So, for example, the current word is love. So, with the help of this multi-head self-attention topic, what will happen? Current word is love, let's say, and this is our input sentence. Now, the model will decide which word in the sentence are more important for understanding the love word. So, this is the overall idea which we are going to understand today. And how encoder learn relationship between words? So, to learn the relationship between the words, the encoder use three different matrices, which is query, key, and value. Query, key, value matrices. And now let's understand this step by step. So each token performs three jobs. Okay, so in our case, we have 8 tokens. So all of these 8 tokens will perform three different jobs. First is query, second is key, and third job is value. Query simply means that each token asks a question to itself, that what kind of words I should pay attention to. For example, in our sentence, so take the example of this token love. So the query of love is basically asking what kind of words should I pay attention to in this sentence. And key simply means key is like a identity card of every word. Here, each token says that this is what I am about, this is what I represent, and keys are used to match with the queries to decide the relevance. And then the third job is value. Value contains the actual information of the token. So basically, here each token is saying that if you attend to me, this is the information you will get. So let's try to understand this with real life examples so that you'll get a proper idea what query key and value is. Guys, I'm going to share one example. This might not be a perfect example, but this will give you a idea. You will understand properly what query key and value is with this example. So think about, you are searching a video on YouTube. So the query is user. Suppose we are searching the video on the YouTube. So query is user, because user is asking to itself what I am looking for. When you search on internet, you type some topic now that this is what I'm looking for. So user is a query on YouTube, and query is asking to itself what am I looking for. And now let's discuss keys. Keys are YouTube video titles which describe what each video is about. And we are using keys only to check the relevance with the query which user typed. You are a user, you are searching something on YouTube. When you search something on YouTube, you get some video suggestions, and keys simply means the video titles, and we are using them for checking the relevance with the query. Now let's see the third matrix, which is value. Now the value is basically the actual video content, the information which you get if you attend to that particular video. So this is what query key and value. Now we understood the basic idea of query key and value. Now let's move forward and let's try to understand this query key and value in detail, and let's see how self attention is actually computed. So our example sentence is, my name is Aarohi and I love coding, and these are the 8 tokens we have. And after that we performed embedding and positional encoding, and after performing element wise addition on it, we got this matrix. This we already have, this we have learned in the previous class. And this is the input. Now this is the input to the encoder of the transformer. This simply means that X is a matrix of real numbers. R means real numbers, and the shape of that matrix is 8 into 4. Why 8 into 4? Because we have 8 tokens in our input sentence, and 4 simply means the D model is 4. So this simply means that the input to the encoder is this matrix, the matrix with the real number, and the shape of that matrix is 8 into 4. Here, each row represents one token, means each row contains the meaning and the position of the token. So we can write it like this also, right? X1, X2 up to X8. So we are starting from X1. X1 is the first token, and then the second token, like this we have 8 tokens. So we can write the input like this also. So X1 is my, X2 is name, X3 is, and in the same way, X6 is I, and X7 is love, X8 is coding. So when we stack these vectors, so this is how it looks. And guys, query key and values are not learned directly. So basically, in every encoder, I have told you that there are 6 encoders, right? Stacked one after the other. So in every encoder, there are 3 weight matrices. One weight matrix will be for query, another weight matrix we will have for key, and then the another weight matrix will be there for value. So like this, we will have 3 weight matrices where WQ is this, WK is this, and WV is this. Now in all these, you will see the shape D model into DK, D model into DK, and then D model into DV. So what is this DK and DV? Let's understand this, and then we will come back to this section again. DK simply means the size of query and key vectors inside one attention head. So guys, see here, for this, for query and for key, we are using dk, and for value we are using dv. So dk simply tells the size of query and key vectors. Okay. And suppose if d model is 512 and the number of heads is 8, then dk will be 512 divided by 8 and you will get 64. So dk will be 64. This is how you get the value for dk. What we did, we divided 512, which is a D model, with the number of heads. Suppose the number of heads are 8, and then you will get 64. Okay, dk, the value of dk is 64, and the value of dk and the value of dv will always be less than d model. Dk simply means these many values you are going to have in each query vector. So guys, remember when we performed this embedding and embedding on all the tokens, and then we performed positional encoding, and then we performed element wise addition on it, what we got our embedding vector, and the size of that embedding vector depends upon which value, depends upon a d model. But the query, key and value matrices which you are going to get, for that, how many columns you're going to have in each row, means for each token how many values you're going to have, that depends upon dk. So this is how you get dk, and the value of dk will be less than d model. So from this dk we can say that the query for each token and the key for each token will have 64 values, and you can write it like this. Now what is dv? Dv is the size of value vector, and this value vector will actually contain the actual information. And guys, this dv mostly is equal to dk only, but it is not mandatory. The value of dv can be different from dk. And now if dv is 64, then we can say the value vector for each token will also have 64 values, right? So value vector for each token will have 64 real numbers in it. This r means real numbers, right? In the same way, the query vector and the key vector for each token will also have 64 values in it. Now let's talk about the weight matrix shape. So you know wq is weight matrix of query, wk is weight matrix of key, and wv is weight matrix of value. So suppose you have a sequence of n tokens. That means this will be your query, this will be your key, and this will be your value. In our case, if we talk about our inputs in tens, how many tokens we have? We have 8 tokens. Then that means at the place of this n, you will have 8. That means for query, you will have 8 rows. For one token, there will be one row, and that row will be the query of that particular token. In our case, how many tokens we have in our input sentence? We have 8 tokens. So for us, the query, key and value will be like this. So our query weight matrix will be of size 8 into dk. And what is the dk value we got if the d model is 512? 64. That means our query matrix will have 8 rows, one row for each token, and that row will have 64 values because the dk is 64. And for key also, we are going to have 8 rows, and in all those 8 rows we are going to have 64 values. And for v also, value matrix, weight matrix also, we are going to have 8 rows, and the dv will be the dv is 64 over here. So like this you will get 3 weight matrices for query, key and value. So guys, till now we have understood what query, key and value is. We understood d model, we understood dk, we understood what dv is. Now let's combine all these topics together and understand the concept. So now what we want to perform the linear projections. Linear projection means we want to apply the linear transformation to get the query, key and value. And I have already told you that to get the query key and value, we will use these things. So to get the query, what you will do, you will multiply the input with the weights of query matrix, and to get the value, you will multiply the input with the weight matrix of value, where WQ is this, WK is this, and WV is this. So now let's substitute the shapes. So X is the input to the transformer, and the input to the transformer is the output of positional encoding vector, which is of shape 8 into 4. 8 is our number of token in the sequence. So N simply means the number of tokens into the number of tokens in the sequence. So which is N into D model. So which is 4 if we talk about our example. So N into D model is over here. And then the WQ is D model into DK. Guys, remember the query matrix or the key matrix or the value matrix, it will be a D model into DK. Now you can write it like this, and inner dimension D model, you can cancel it, and you will get N into DK. So guys, here see that rows are not changing, only columns are changing, because rows represent the tokens in the sequence. So rows are not changing, only the columns are changing. Earlier, we were having different number of values, and in query key and value matrix we have different numbers, different values. Okay, the count is different now. Now our matrix, query key and value matrix, will be of shape N into DK. So guys, the core concept which is used in creating this query key and value is linear projection. Linear projection simply means, mathematically, this is what we have used. So this is what linear projection means. And linear projection simply means that we take the same input vector and we look at it from three different learned perspectives. So suppose for token love from our input sentence, and now this same vector will be used three times. One time as a query, one time as a key, and one time as a value. And in transformers, this transformation is called matrix multiplication, and this is how we compute it. So the token love is same, but the model looked at it in three different learned ways to decide the relevance, matching, and the information flow. Guys, here one very important clarification, that the vector, the input vector, the vector of love or the vector of any other token does not change. The weight matrices change, okay, epoch by epoch, which means the same input vector but different learned matrices, different outputs. Different output means different query key and value for same vector. For love vector, we are going to have query key and value. The input vector for all these three matrices will be same, which is the embedding vector of love, but query, key, and value will generate different vectors out of it. Let's understand it with example. Let me explain you this with example. So suppose you have a vector of love. This is the embedding vector of love. Okay, so this is the fixed vector. So nothing modifies it directly. So everywhere it is going to be same. Okay. Now what is exactly changing? Let's understand that part. What changes is how we use this vector. So we are multiplying it with three different matrices like this over here, query, key, and value. So the same embedding, the embedding of love token, is getting multiplied with the weight of query matrix, weight of keys, weight of value matrix, right? The X love token have the same value in these three scenarios you can see here. What is different then? Vector is same, but the weight matrices which we have for query, key, and value are different. Okay, guys, let me explain you this mathematically with the help of example. Okay, so we will see for one token only. So we are talking about the love token. So let's talk about that only. We will have three weight matrices. So these are the three weight matrices now. So right now I'm just writing the simple numbers to make you understand the concept. So this is how you calculate the query, key, and value. Now, if you'll notice, the query, key, and value vector for love token have different output values, right? Why? See, the input embedding is same for all these three, but the weight matrix of query, key, and value is different. So that's why the query, key, and value will have different values. And guys, another thing to remember, that you will use the same weight matrix of query, key, and value for all the tokens. What I'm saying is that the weight matrices, the you will have one weight matrix for query, one weight matrix for key, and one weight matrix for value. So these weight matrices will be same for all the tokens within one encoder. Right now we are talking about one encoder only. So inside one encoder, you will have only one weight matrix of query, one weight matrix of key, and one weight matrix of value inside one encoder. When you will work on another encoder, over there you will have a different weight matrix for query, key, and value, and inside that encoder, that one weight matrix which you have for query, one weight matrix for key, and one weight matrix for value, that weight matrix will work on all the tokens. And this weight matrix is random initially, and with training these values are learned. This is how you create query, key, and value matrices for all the tokens, where each row corresponds to one token. And during training, model will take the predictions, model will calculate the loss, then gradients are propagated, then weight matrices, which are wq, wk, and wv, are updated epoch by epoch, and these updated weights are shared across all the tokens. And when we use the updated weights, each token still produce a different query, key, and value vector. And this is because each token has a different input vector. So same learned weights for all the tokens inside one encoder, but different input token vectors, right? So you will get different query, key, and value outputs. Why weights must be shared across all tokens? Because model should apply same rules to every word regardless of position. So, guys, that's it for today's lecture. And I hope the concept of query, key, and value is clear. But guys, if you feel that if anything is missing, then please mention in the comment section, because right now we are studying about transformers only. And if there is anything which I've missed, then I'll cover that in the next lecture. And in my next video, we will continue the topic from where we have left in our today's class. So I hope this video is helpful.